Okay, so here's an example of how you might use Coulomb's law to determine the vector force between two charges. So what we have here is a charge of -1 microcoulomb. Change my pen here. -1 microcoulomb. And another charge of -2 microcoulombs. And we're asked to determine the vector force acting on the -2 microcoulomb charge due to the -1 microcoulomb charge. And we're given additional information, which is the angle between the separation vector and the horizontal is 45 degrees. So this angle right here, which we're going to call theta, is 45 degrees. Okay, so one piece of information that tells us is that each of these sides, so if we were to draw a triangle, I'm going to change the pen color here so we don't overlap too much. This side and that side are exactly 2 times the sine of 45 degrees, or 2 divided by root 2, and 2 divided by root 2. So now we have to determine what that vector force is. We've done a little bit of geometry. We're going to do a little bit more drawing on this picture. So we know that these two charges are both negative, and therefore the force that acts on the -2 microcoulomb charge is along the line and points away. So therefore it must point in this direction. So the force that it experiences, F, points up and to the right. So now we can start to apply a coordinate system to really understand that. And so it's good enough to say, well, let's put the origin of coordinates on the -1 charge. So here is the plus x direction, here is the plus y direction, and we're going to label this location right here to be the origin, so that'll be 0, 0. And therefore, this -2 microcoulomb charge exists at 2 root 2, comma, 2 root 2 in the xy plane. So now we have all the information we need to calculate the force. So we want the vector force, which is equal to k times q1 times q2 over r squared r hat. And so k we know is 9 times 10 to the 9. Whoops, that looks really bad. Let's make that an e. Let's just do this. 9 e to the 9 newtons meters square per coulomb squared. We know that the first charge, q1, is equal to negative 0.1 e to the -3 coulombs, and q2 is equal to negative 0.2, e to the -3 coulombs. Now what we have to do is figure out what is r. Well, the charges are separated by 2 meters in the linear in this linear direction, so they're actually separated by that amount. And so the magnitude of the distance between them, which we're going to call magnitude r, is equal to 2 meters. But the r vector that actually separates them is 2 over root 2, comma, 2 over root 2 meters. So that means that the r hat vector, which is equal to the r vector divided by its magnitude, is 2 over root 2, comma, 2 over root 2 divided by 2. And so the r hat vector is equal to 1 over the square root of 2, comma, 1 over the square root of 2. And if you take the magnitude of that, you'll find that it's 1. And it has no units because it is a unit vector. It's unitless. These meters cancel. So now we have everything we need to compute this force in its full vector form. So F, the force, is 9 e to the 9 Newton meters square per coulomb squared times negative 0.1 e to the minus 3 coulombs times negative 0.2 e to the minus 3 coulombs divided by 2 squared, and that's meters, mind you. And if you look, then the meter squared cancel with that meter square, the coulomb squared cancels with those coulomb squared, and we multiply that by the unit vector 1 over the square root of 2 times 1 over the square root of 2. Now I haven't worked out the numbers exactly, but what you can see is that that negative sign will cancel that negative sign, so that'll be a plus and a plus, and these two vectors are both plus and plus, and that gives us something that points up and to the right. So if you do that, if you finish that calculation, what you'll find is that the f vector has a positive fx component and a positive fy component, which is a nice check to make sure that we got the right thing. Alright, so in the next screencast what we'll do is we'll calculate the force that acts on a charged particle due to two charged particles, and we'll have to deal with vectors in 2 dimensions.